этого доклада, что многие хотят на русском, но как Джим Андерсон я не готов докладывать на русском. Вместо я буду докладывать на английском с азербайджанским акцентом. Доклада So I will talk about multi-scale model reduction for porous media application. You can find all the papers related to this topic on my website. And so what is multi-scale? So I'm going to give a little introduction because the audience is very broad. So first of all, what is multi-scale? So this picture is taken, I took it from Google Earth. You can see that here Earth is taken at 3 different resolutions. So you have a resolution 100 kilometer, and then I zoom in and zoom in. So what you see here, scales. So scales mean that you see a lot of like different colors, different what you call heterogeneities. And this is very common in many applications. For example, the same application in porous media. If you take a porous rock at different resolution, you take a very poor resolution, you can see a lot of heterogeneities, small scales, and then you go to the larger scales, you see similarly very complex heterogeneity. So the name is basically here that I'd like to develop methods for the complex heterogeneous problem with high contrast. So I will just say few more words about this to make it clear. Or for example, if you take this example, you see rock with cracks. These are the cracks, and you see a lot of scales. For example, in a crack, the conductivity is very large, while background is very small. So this is what we call high contrast. So idea is that we'd like to develop methods that we can solve this problem numerically. So these are very complex problems. We want to solve this problem. So first thing you can ask me, for example, if you're a petroleum engineer or subsurface person, why do I need all this? How can I get all this information? Now, how can I find all this information? In fact, nowadays it's very common. For example, if you look at the reservoir, there's a lot of data collection going on. So when you have a very large reservoir, say several kilometers, you can get the samples of the very little size, and you can zoom in and you can actually reconstruct all the pore scale. So you can ignore it, just build very coarse model, but that's something we don't want to do. We want to build these models at a very fine detail and be able to solve it. So what is the multi-scale functions? Just start with something very simple. So this is a function of 2 scales. You see, this is a 2 plus x sine x over epsilon, where epsilon is 0.01. So you can see here 2 scales. One is basically this is scale 1, and a second scale is epsilon. These oscillations is occur at the scale epsilon. So I can put many of these oscillatory functions together and get a picture like this. So you see very small scale. Scale is basically the variation of order 1 you see at the scale epsilon. But what I'm interested really for more complex field when I don't have scale separation. So there is scale separation because I have 2 scale, 1 and epsilon. But if you look here, for example, this is conductivity fields, where you have say white is high, black is low. You can see all kind of sizes here. You can see small sizes, bigger sizes, and all kind of sizes. To make it, you can idealize this picture. For example, imagine that you throw very, very thin, long channels. This is called channels of high conductivity into your domain. So what's happened that then you can actually introduce many, many scales, which is related to the length and to the width, right? And in practice, really, you have for example, if you have a fractured rock, you have a small fracture, you throw it, and then they form those channels. So you really don't know what are the scales. You just know there are a lot of scales. So what I do, I basically consider equation when those fields I show, they are coefficients. So I don't just study the fields themselves, just multi-scale expansion, but what's happened to the solution. For example, I can have a diffusion equation where diffusion coefficient is that field I showed you. I can have a, say, I can have a Stokes type equation when this is reaction coefficient is that heterogeneous field. I can have a wave equation and so on and so forth. I can have a domain with holes with a lot of scale. So this is, but the key word here, we want to have we will work with the cases when we don't have a distinct scale. And what is this model reduction that I want to talk about? So imagine now I have this very fine detailed model that has many, many degrees of freedom, say 10 billion, 100 billion degrees of freedom that I can't afford to solve. But then I have some inputs, for example, right-hand side, F, right? And I'd like to solve this problem. So my goal is to find a simpler model, coarser model, so that I can solve that. If I solve this coarser model with the same right-hand side, I get an output similar if I solve it with the very detailed fine model. Right? So this is called general model reduction. So I want to reduce the model. I want to go from very complex model to simple model. So model reduction, here you can divide it into the basically two categories, which is one is local, and I will talk about a local. Basically, idea of the local, I'd like to go divide domain into computational grid and try to reduce model there at that level. Or we can talk about global model. So let me start with just an example of a local. In a local, there are two: numerical homogenization and multi-scale. This is basically what I will talk about, but just I will say a few words about numerical homogenization, because this is very important. So numerical homogenization actually goes back to homogenization, and this is a well-developed area. I think I developed actually in Russian school, and I was in Moscow actually when I studied a lot of homogenization. So what homogenization does? So it's usually considered a problem with scale separation. Let's say I'm solving this diffusion equation where coefficient varies in two scales, 1 and epsilon. That you see, 1 and epsilon. So I have a 2 scale, but this is called separated scale because epsilon is much smaller than 1. So what you can do in this case, since this is there's a big theory called homogenization, you actually introduce the fast variable yx over epsilon. In a sense, this is your domain. You divide your domain into the computational grid. In each computational grid, you have a little period where you take a sample, and in that sample, you solve the local problem like this. So actually, you can derive it. These are the more result of homogenization for a simple equation. You derive this. You solve this local problem in each of this period. This is period, and then you take this solution. You average the solution time. This fact itself is not important. Just the average the solution gradient, and you get what's known as an effective property in each block. So in each block, you replace media by effective media. So this is also known under effective medium theory. There's many theories. But homogenization is one of the very rigorous theories. So it's basically homogenization says that if I solve this n and I know this u0, then I can approximate my solution with this two-term expansion, which is u0 plus epsilon n grad u0. So let's look at this expansion. So this top is the same I took from the previous slide. So I take a gradient of this term, gradient of this u hat. So gradient of u hat, if I take the gradient of u hat, so first I take gradient of u0, and when you take a gradient of this term, the dominant term when you differentiate n with respect to x, right, which I call it y. So these two dominant terms look like this. Now what I do next, I take this grad x u0 out, and I have this thing in a parenthesis. Right? So what it shows, so then you note that since u0 is a smooth function, you can approximate u0 by a constant inside each block. This is called coarse block. This is your computational domain, so error you make is order h. But what is important here that this shows that my solution has actually 2 degrees of freedom. By using homogenization, I'm assuming my solution has 2 degrees of freedom in each block. So this is actually continuous. So there are theories that extend homogenization, which basically take a bigger periods. This is period. In engineering, it's called representative volume. So you enlarge this because you may think that this sample not enough. Let me take bigger. Or you can actually take a whole coarse block, which basically petroleum engineers do. So if you have a domain, you divide domain into a computational grid, and in each grid, you basically want to compute effective properties, and you follow your homogenization theory. So what homogenization theory tells you, that I will go and solve two local problems. So I will solve the local problem with x1 boundary condition. So x is x1, x2, and then x2 boundary condition, and then take an average of the fluxes. Just like I showed you before, you get a tensor here for each block. So in each coarse block here, I had a lot of variation in my coefficient, but I replaced it by a constant. That's called effective property, right? But now if you look at effective property, to compute this effective property, I need two solutions. So this is again tells me that actually I need really this by using this effective medium theory, I'm assuming my solution space has 2 degrees of freedom. And this is all breaks down as soon as you don't have scale separation. This is what the key is. But this homogenization theory is very rich, so you can go, for example, some problem that don't have periodicity. For example, you have homogeneous domain and heterogeneous domain. So when you derive homogenization, you observe that you have another parameter that comes because this is a Joseph Beaver. So that's come by solving another cell problem. Okay? So basically, what point I want to make, anytime you have effective, if you have a say permeability or conductivity at the point, for example, here, right, there is only 3 numbers here, 3 distinct numbers, K1, this is symmetric tensor. And this assumes that locally you have 3 degrees of freedom. And the reason you have 3 degrees of freedom because you have a periodicity, you have something very, very simple micro scale. Otherwise, you will not have 3 degrees of freedom. Okay, so anytime you have any homogenization, anything similar, you get effective medium theory. Just go count number of effective medium parameters. That's an assumption how many degrees of freedom your solution local has. And these are all breaks down when you don't have scale separation. And this is where we need new methods. And that's what I've been working. So as I say, many applications don't have scale separation, and then we cannot use homogenization. And we need to be able to still somehow capture. If I want a method that can act like homogenization, but like this is a problem when homogenization, for example, breaks down. If I have a high conductivity cutting through, then I want in these examples, my method also work to identify that I need here not 2 degrees of freedom, but maybe 5 or 7. I want method that finds that for me, not that I write a macroscopic equation and think how many parameters I need to identify. So here we use multi-scale finite element framework for a beginning. So let me just introduce this briefly. It's a simple concept. So let's say I'm considering, again, I'm going to do simple equation, diffusion equation with heterogeneous coefficient. So what you see here, basically I have the fine grids. This is I call fine grid, and then I overlay coarse grid. So imagine your fine grid, very fine. There's like 1,000, say 10,000 by 10,000. You cannot solve it, so you overlay with a coarse grid. This is a coarse grid. So then in each coarse grid, instead of computing effective properties, I'm going to try to build finite element basis. So this is like a Yalcin approximation. So my goal is to find this finite element basis. In this case, I'm going to first start with 1, such that u minus u star is small. So this would be like your approximation theory type. Right? It's a question. What is this phi? And the coefficient varies. The coefficient on a fine grid varies a lot, just like you saw. So one simple basis, so usually this basis function in finite element, they are hat functions. What I want to do now, I want to change a hat function, put some oscillation in a hat function. So this is what you see here. So I can do the following. I can take my hat function, which is 0 on the outer boundaries, and linear in this cross, and 1 here. So I'm going to keep all that the same, except I'm going to here solve the local problems. Okay, so I'm going to solve the local problem inside. So this is my hat function going to. Okay? So I'm going to have this multi-scale basis in each coarse block. So coarse, again, I use coarse. This is a coarse block. So you have a lot of variation within coarse block, but I'm trying to reduce my model. just have one basis. And then I'm going to look for the solution in terms of linear combination of this u, right? In this phi, ui, phi, and I will substitute in the equation and project and multiply by a test function. So this is what I have now. Now this approach, everything is applies to complex grid, 3D, and so on. But so first you can probably recognize that I use one basis per course node. So it's like homogenization. I have only, in each block, I have 4 functions, right? And I was against this. I don't want to have a few functions. I want to have a rich space. But let's just take this for a minute. But you can show actually the approach I showed with basis function is similar to numerical homogenization. That's what it says. But the one key things here, and this is many years of research that people work, actually this linear basis function that you start building here, they are not right because solution not linear along these edges, right? For example, if I have this domain, this is conductivity. I have a very high conductivity here. And once, the solution not going to be linear here. Here is a solution. It's not linear. It has a little bit wavy shape. So this is what multi-scale solution look like. So this is actually, this is a big issue. So how can you improve the boundary condition? And approaches here goes something called oversampling. So if I want to build a basis function, and this is very common concept that we use all the time, even in different methods. So if I have a course block here, K, and I'd like to build a basis function, what I will do, instead of putting linear boundary condition anywhere here, I'm going to put linear boundary condition in this larger domain, S. And then solve a local problem in this larger domain, S. And then take only interior information in K and build a basis function. Now, this is how oversampling works. This itself is good, but still this method improves the error, but it still has a large error because the space is limited. You have only one basis function per vertex. But inside you have a lot of variation in coefficients. So how can we actually get the right space by enriching? So this is basically what I've been working over the maybe last 4 years or so, and I developed this general framework and used it for many applications. So to explain it briefly, so basically, so we start usually process. Anytime we solve the problem, we divide it. This is very common in model reduction in an offline and online state. So let's say that I don't know right-hand side, F. I don't know my right-hand side, F. But I know my coefficient. So I'm going to try to build something in offline state so that if you give me F, I can solve this problem very fast, cheap, at the cost of course grid. So here's just basically outline of this generalized multi-scale. So I will start with there's two things. There's two things very critical, which I will talk here. So I will start with a coarse grid. Then in each coarse grid, I will build some type of a snapshot, and then I will use some type of a spectral problems to identify my coarse spaces. This is basically two main things. And in the next slide, I just give an overview a little bit, and then maybe just go over the slide. So let's consider, basically we start with some differential equation. For example, LU equal this LU equal divergence K grad U. So K is heterogeneous. I have a fine grid where K varies from point to point, but I want to solve problem on this grid. This is called coarse grid. So first thing I do, in each coarse block, I build some snapshots. So I try to build a large space that will give me some good error if I solve my problem in that space. So this is not the space we want to use. That's why I call snapshot. So this is, I just want to throw a lot of function. It's like it will be, say, dictionaries in approximation theory language, but it's still not a very large dictionary. I try to build in each course block here, which I show you what is this. Then once I have this, then I'm going to use some type of a spectral decomposition. And this is also, we have to be careful what spectral decomposition in this space to identify this basis function. Basically, if I have a scale separation, I'd like to have one basis function like I showed you. Otherwise, I want to have 2 or 3. I don't want to have too many basis functions. Of course, I don't want to use this method for problems that don't have multi-scale or has very weak multi-scale. I want to use for a problem where there are a lot of scales. And then we derive a priori error estimate, but then before a priori estimate. So we use this basis function and solve the problem. Right? Once I have my basis function, say I have a 3 basis function here, 2 here, 4 here, 1 here, I just sum them, and there are many, many ways to solve it. I plug it in the equation and I solve it. But this is not all. So what's happened then, we have to develop error indicators, which actually go and look at the region and say, do I have enough bases, or I should add one more basis? This is called error indicator. So we develop error indicator and add this in selected region, because we never know how many basis function we need in what region. Then there is a more coming, so we basically have to develop something that sometimes this basis function, since they build locally, they don't take into account global information. You may want to build online basis function. So basically in online stage you build a basis function. There's issues, some other things, stability, sparsity, and so on. So let me just show you snapshots first. What is snapshot? So this is my domain, this is my course block. So in each course block, so I want to build snapshots. So simple, very simple snapshot is all possible fine grid vectors. Let's say this is 20 by 20. There's a 400 vectors, 1, 0, 0. So unit vectors, just my unit vectors. This will be a simplicity. We usually don't use it. This is not a very good thing. But other things, I can go in a boundary and put a unit force in every boundary node, like you see here. And then solve local problem, and 0 everywhere else, solve the local problem. This is another. But this is also not good, because why is it not good? Because by doing that, I'm assuming solution can be inside domain, 1 here, 0 everywhere else. But solution has some structure. Solution can't be just 1 at one point, 0 everywhere else, right? Solution has some structure. And here comes a lot of oversampling ideas. You can do the same thing in a larger domain and throw away everything here. In fact, this can give you much better convergence. It's like you have a harmonic functions, and then you look the n width inside the domain. If you have a harmonic function, we know that n width, right, in the middle of the domain, it's exponentially small. So this is decaying. So these are type of things here also use and helps a lot. So, but then there are too many of them. I don't want to, for every node, solve a problem. What you can do, you can, for example, if I want a 2 basis function, I can just put random numbers on a boundary, but and then solve local problem, but only solve 6 of them. And then I will do spectral decomposition and find 2 dominant eigenvectors. So this goes to randomize SVD, those things. So you can actually, it works pretty well, and you can prove it. So these are snapshots. So what about offline space? This is a multi-scale space. So I'm not going to talk much here because it really depends on a problem on discretization. But typically, the local spectral problems involve some two matrices, right and left, and it can be very complicated sometimes how to build the spaces, depending, because in numerical analysis you need certain properties. For example, if you want a stability of your bases and so on, you have to somehow impose it. So a lot of these things can be complicated, but the simplest thing will be you just use 2 local eigenvalue problems, 2 matrices, right, or 2 bilinear forms, and use them to find dominant modes. And these are usually, first of all, they're very important how to choose them, because we know solution not smooth, and we cannot go to higher derivatives. So if I go to higher derivative, I typically get my polynomials and so on. Here we cannot go to higher derivative. If you remember that x over epsilons start coming up. So then it depends on discretization and so on. So this is just intuitively what we do often. For example, if I have a long features, what I call channels. Channels are the high conductivity region that are very long. If I have a coarse block, if this is my coarse block, for example, I can homogenize all these inclusions, this is inclusion, into 1 basis function. So I just need 1 basis function for all the 6, 7 inclusion, but I need to represent each channel separately. But it comes out from spectral problem and so on. So how does it work? There's many papers we've written. For example, if I look at the two-phase flow, so this is water displaced oil. So it's like your typical displacement problem. So you have an oil and you're injecting water, you're displacing the oil. So you have two coupled equation, what's called pressure and saturation. So I'm going to apply multi-scale here, in this equation, and show the result. So we basically take, say, problem 200 by 200 resolution, and I'm going to use a 10 by 10 coarse block. Okay, so this is my permeability field. This is some benchmark permeability field by SP Society. You have very high channels conductivity and very low. So if I have a 200 by 200, you basically divide it by the 10 by 10. So each block has a 20 by 20 resolution. Each block has a 400 degrees of freedom. But I will use only 2 here, or 4. And this is what's happened. This is a solution reference. So I'm injecting from the top. This is saturation profile at 3 different times. So water infiltrates. This is if I use 2 bases, if I use 4. You see that 2 does very well, except it misses some features here, but 4 is very good. So this way I saved it. Instead of 400, I use 4 degrees of freedom. Okay, so let me skip this for interest of time. So adaptivity, no, I still have. Adaptivity is another important thing. We basically have to detect a region where we need more basis function. And this actually can be not trivial. For example, the region you see here, it has a lot of inclusion. But this region actually doesn't need many basis functions, because this region is, you can homogenize it. You have 1 degree of freedom. But a region like this, for example, you may need more basis function. And this is all done through the arrow indicator, which involves spectral information. These are the eigenvalues. And this is basically how the convergence rate usually goes. How fast spectrum decays on that local eigenvalue problem, that more or less tells you your convergence. Build your local basis. Sometimes you use only small information. So this is actually just, so the multi-scale method that we build, there are some ingredients. For example, these are very fundamental no matter what you use, adaptivity, randomization, online basis, and then we apply. And we've done many applications, wave, perforated media, fractured rocks, poroelasticity, and so on. So basically, the bottom line is that these methods are good when your problem multi-scale. So it doesn't work. It's not. You don't want to use this if you have a very few scales here or there. You have a 1 inclusion or something. You want to use it when you have a lot of scale and then cancel out, so you can do that. And the important thing is local. You have to do it locally, so that in each block, it's like in homogenization, I can separate my basis function and solve the problem. Thank you.
Thank you very much.
Head functions by some more smooth functions. You get, of course, a larger support, and you have also more unknowns, more degrees of freedom. How can you? Are there some strategies how to determine?
So typical solution is like a sine x over epsilon. If you use a smoother function, you go to the higher derivative, and more derivative you take sine x over epsilon, it's become worse and worse. So it's actually not a good idea to use polynomials because function not smooth. It's like a Gibbs phenomenon. I mean, in that sense, we have at every block, at every point, we have something like Gibbs phenomenon. Not just 1 point, but every point.
Yeah, if you, for example, use a third order line or something like that, or a second order line. So
no, the bigger support is okay, but the spline itself, no. You need to build the functions that fit into the multi-scale structure. It's like if your coefficient vary, which I showed, they have to also vary. Otherwise, you will need a lot of bases. It's better just to go and do everything on a fine grid.
Okay, thank you.
Yeah.
Okay. Yes.
Yalcin, какую размерность задач, вот конечный элемент программы используют, какого порядка размерности, какая обычная техника, компьютер какие используют?
Компьютер параллельный иногда просто find метод разные конечные элементы. Galerkin, discontinuous Galerkin.
üstüne gelir.
Aradığınızda 100 dəfə, 200 dəfə şeydən böyük olur. Dolabda böyükdən.
So thank you very much.
Thank you.